Hey calculus class, today we're going to learn topic 57, polar coordinates. So what are polar coordinates? So there are two different coordinate systems to describe one specific point. So the one that we're most comfortable with is of course the x, y coordinate system, the Cartesian coordinate system. So if someone wanted to get to the point x, y, we would tell them to go x units horizontally and y units vertically. So we would go x units horizontally, y units vertically. Now, of course, the best way to get to the specific point would be to start at the origin and walk towards the point. But how do we describe to someone how to get there? So the best way to do that is if you're standing at the origin, you can turn your body so many degrees, or in our case, radians, and then you can walk at that angle to the specific point that we want. Well, we of course call that angle that we're going to turn our body theta, and that distance is going to be r. So we would tell them to walk r units in the theta direction. And we're using r because if we think of circles, it would represent radius. So that means that the point x, y in our Cartesian coordinate system would represent a point called r, theta in what we call our polar coordinate system. So in the Cartesian coordinate system, how would you describe to someone how to get to the point 3, 4? We would say walk 3 units right and 4 units up. Now in the polar coordinate system, how would you describe to someone how to get to the point 3, 4? Well, we know we need to turn our body so many radians and walk so many units towards 3, 4. Well, how am I going to actually calculate those values given just the 3, 4? Well, if you notice, we have a right triangle. So can we find the value of r? You should be all saying, yes, Pythagorean theorem. So we have that r squared equals 3 squared plus 4 squared. So when I solve for r, I get r equals 5. So I have a radius of 5. Now you should be thinking to yourself, how am I going to get theta? Well, you should be thinking, oh, trig. Well, let's see. I can use any of the 3 trigs, tangent, sine, or cosine. But since I was given the 3 and the 4, so the opposite and the adjacent side, I'm going to go ahead and use tangent. So tangent theta is equal to 4/3. In order for me to find theta, you need to use your inverse tangent. So theta would equal the inverse tangent of 4/3, which will give me 0.927 radians. So what this means is that the point 3, 4 in our normal Cartesian coordinate system is equivalent to the point 5, 0.927 in the polar coordinate system. And we would tell somebody to rotate your body 0.927 radians counterclockwise. So notice we are turning counterclockwise from the x-axis and walk 5 units. Now, how do we plot polar coordinates? When plotting polar coordinates, it is best to think about the unit circle and always start with the angle measurement. So instead of this being your normal x, y grid, you're thinking in terms of the unit circle. So 0, pi over 2, pi, 3 pi over 2. So if I wanted to plot the point 3, pi over 4, that means that I want to go to the angle pi over 4 and go towards the angle 3 units. So that means if I'm standing here at the origin facing the 0 angle, or the 2 pi angle, I'm going to turn my body counterclockwise pi over 4 radians. So that I am now looking along this line. And I'm going to walk 3 units towards that angle, which will give me a dot right here. Now, if the R value stayed the same, but the angle changed, what do you think will happen? You should be thinking that you would be rotating around a circle that has a radius of 3. Now, what does it mean if the radius was -3 and the angle stayed the same? Well, the radius would still be 3, but be pointing in the opposite direction. So that means that I would be standing here instead of right here. Still have a radius of 3. I am just now in the opposite direction. And of course, this is at the angle 5 pi over 4. So in other words, polar coordinates have 3 possible different ways to write them. So you have the given form, which we were given 3 pi over 4. And then when r is opposite, which was -3 5 pi over 4. And that just basically means add pi to the angle and change the r value to the opposite. So when I want to plot -3 5 pi over 4, what that means is I'm going to rotate my body to the angle 5 pi over 4, which is this green dotted line. And since it says that it's a radius of -3, that means I'm going to walk in the opposite direction. So I would still land here. Now, if this was a +3, I would walk in the direction of 5 pi over 4 and would land here. Now, the third one is when r is the same, but we go around the circle more than once. So basically, if you were to rotate your body a full 360 degrees, aka 2 pi, you would just add 2 pi to the angle, so that you would get 3, 9 pi over 4. All right, so for this example, I want you to try this on your own. Plot the point -4, 5 pi over 6, and then find 2 other pairs of polar coordinates of this point. All right, let's see how we did. So first thing is I want to go to the angle 5 pi over 6. And since I have a radius of 4, I'm going to have to go 4 units. But since it's negative, I'm going to go in the opposite direction of 5 pi over 6. So that means I'm going to be right around here. That means that one of my other coordinates for this polar coordinate would be the point 4, 11 pi over 6. So if I was to rotate my body 11 pi over 6 radians and walk 4 units that direction, I would land in the same spot. And then the other option is -4, 17 pi over 6. So basically, if I was to rotate 360 degrees from the 5 pi over 6 and then go the opposite direction, I would still land in the same spot. All right, go ahead and try this example. Plot the point 2, -pi over 7 and find 2 other pairs of polar coordinates for this point. All right, so this time my angle is -pi over 7. So that means I'm going to move pi over 7 in the clockwise direction. So I would land approximately right here. And I'm going to go 2 units towards the -pi over 7. So here is my plot, my point. Now if I was to go in the opposite direction, I would be looking at the angle 6 pi over 7, but I would need to go -2 units from that angle. So I would still land in the same spot. So my other point is -2, 6 pi over 7. And then if I was to go another 360 degrees, I would be at 2, 13 pi over 7. All right, now let's look at converting between rectangular and polar coordinates. In general, we can convert between the Cartesian and polar coordinate systems quite easily with just a few tools. So we already have this typical picture, which means we have the Pythagorean theorem, which is r squared equals x squared plus y squared. And that we had that tangent theta equaled y over x. And we also have that sine theta would equal y over r. Therefore, y would equal r times sine theta. And we have that cosine theta is equal to x over r, which means x equals r times cosine theta. So these are the tools that you're going to need to convert between polar and rectangular coordinates. All right, so for example, find the Cartesian coordinates of the point 6, 3 pi over 4. So we have that x equals r times cosine theta and y equals r times sine theta. Well, since we're given r, which is 6, and we're given theta, which is 3 pi over 4, I can find x and y. So x will be 6 times cosine 3 pi over 4, and y will be 6 times sine 3 pi over 4. And after I do reducing, I get that x will equal -3 square root 2, and y will equal 3 square root 2. So therefore, my Cartesian coordinates would be at the point -3 square root 2, 3 square root 2. All right, why don't you go ahead and try this one on your own. Find the Cartesian coordinates of the point -2, 5 pi over 3. All right, let's see how you did. So we have x equals the radius cosine theta and y equals the radius sine theta. So once I plug in the radius and the theta and reduce, I get that x equals -1 and y equals square root 3. So therefore my Cartesian coordinate is -1, square root 3. All right, now let's go the other way. We want to find the polar coordinates of the point -1, square root 3. So this is a little bit more difficult. We have the x and the y, but we need the r. So using the Pythagorean theorem, I know that r will equal the square root of x squared plus y squared. So when I substitute in the x with -1 and the y with square root 3, I get 2 square root of 4. Now I still need the theta. We have that tangent theta is equal to y over x. Well, I have the y value and the x value, and I'm going to reduce that. So now I have tangent theta equals square root 3. So in order to find theta, you can either use the inverse tangent, of course, would always work, or you can think about it more graphically. And since -1, square root 3 is in the third quadrant, that means that our angle would have to be 4 pi over 3. Now within the interval from 0 to 2 pi, there are two forms of the polar coordinate. So we have radius 2 and our angle 4 pi over 3, or we can switch the radius to be opposite, but that means we have to go to pi over 3. All right, so why don't you go ahead and find the polar coordinates of the point 3, -3 on your own. All right, so let's see how we did. So to find the radius using the Pythagorean theorem and solving for r, so you should get that the radius is 3 square root 2. Now to find tangent, we have tangent theta equals -3 over 3, so tangent theta equals -1. And since 3, -3 is in the fourth quadrant, then theta has to equal 7 pi over 4. Within this interval, 0 to 2 pi, the two forms are 3 square root 2, 7 pi over 4, and -3 square root 2, 3 pi over 4. Polar functions. So a function in polar coordinates has the form r equals f of theta. In other words, r is a function of theta. Some examples include r equals 4 cosine theta, r equals 3, r equals -3 times secant theta. Just like with the coordinates, we can convert between the rectangular functions and the polar functions. So Find the polar function given the Cartesian function x squared plus y squared equals 4. Well, we know that the radius squared is equal to x squared plus y squared. So therefore, r squared has to equal 4. And of course, remember that the plus or minus doesn't matter with the radius because radius is representing a length. So therefore, we have an r of 2. Graphically, this is a circle with a constant radius of 2, since x squared plus y squared is your good old traditional circle equation centered at 0, 0. And that's it. If all you were given is r equals 2, that should register in your brain as I have a circle with a radius of 2 that is centered at the point 0, 0. All right. Now we want to find the polar function given the following Cartesian function. All right, so with this one, we have the knowledge that r squared equals x squared plus y squared. And we also know that tangent theta is equal to y over x. So if we notice here, we have that x squared plus y squared equals all of this. So that means that r squared is equal to all of this stuff. Now, since we have that tangent theta is equal to y over x, I have a y over x right here. So I can replace that y over x with tangent theta. So therefore, I can say r squared is equal to 9 tangent theta squared. And when I solve for r, that means I'd square root both sides. So that means that I get r equal to 3 tangent theta. All right, this time let's find the polar function given the Cartesian function of 3y minus 7x equals 10. This time, we're going to want to use the fact that x equals r cosine theta and y equals r sine theta. I'm not using the r squared equals x squared plus y squared because I don't have an x squared y squared in here. So therefore, I can replace y with r sine theta, and I'm going to replace x with r cosine theta. My goal next is to solve for r. So I can factor out an r and divide by the 3 sine theta minus 7 cosine theta to get r by itself. Okay. Now, with the next two examples, we're going to find the Cartesian function given the polar function. So, we're given that r equals 4 sine theta. Well, I know that sine theta is equal to y over r. So therefore, r has to equal 4 times y over r. Notice I replaced the sine theta with y over r. Now I'm going to go ahead and simplify this a little bit. So I get r squared equals 4y. Well, notice I have an r squared still sitting here. But I know that r squared is equal to x squared plus y squared. So therefore, I can substitute in x squared plus y squared in place of r squared to give me a function of x squared plus y squared equals 4y. And I know I'm done because I have no more thetas or r's left in the function. All right, now let's do the same thing, but this time r equals sine theta plus cosine theta. So for this one, I know that sine theta equals y over r and cosine theta equals x over r. So I can replace the sine theta with y over r and the cosine theta with x over r. Since they have a common denominator, I was able to add the two fractions. And I'm going to simplify this to get r squared equals y plus x. And since I know that r squared is equal to x squared plus y squared, I can replace that. And so my function becomes x squared plus y squared equals y plus x. All right, now we're going to do the tricky part, graphing polar functions. When graphing polar functions for this class, you'll want to do the following. First, set the argument of the trig function equal to pi over 2 and solve for theta. This helps us decide on the increments of the graph since it will be easier to evaluate the trig function at these values. Step 2, create a table of values on the interval from 0 to 2 pi. Then plot these points on the Cartesian coordinate system. Then you're going to translate the rectangular graph onto the polar coordinate system. So let's look at an example. All right, so we have that r equals 3 cosine 2 theta. So first thing is I'm going to set the argument equal to pi over 2. Well, my argument is 2 theta, so I'm going to solve for theta. So I get theta equals pi over 4. So this means that we will create a table with theta values in increments of pi over 4. So when I set up my table, I'm going to go from 0 to 2 pi, and I'm going to evaluate at every pi over 4. Now, when I evaluate the r function in terms of each of these theta functions, you should get the following values. All right, so now since you have your table, you're going to go ahead and plot each of these points like you normally do on the XY grid. So that means after you're done plotting, you should have your graph that looks something like this, right? Using this as theta and this as your radius. Now here comes the tricky part. Translating this into our polar coordinate grid. So I'm going to attempt my best to do this by hand on the computer, so bear with me. All right, so I'm going to start off by making my polar grid. And since I'm thinking in terms of angles, this is 0. This here is pi over 2. This one's pi. And down here we have 3 pi over 2. And since I'm going and my radius is staying between 0 and 3, that means the max I'm just going to go on any side of the angles will be 3. So I'm just going to mark off my increments as best as I can. All right. All right, so now I'm going to graph each one of these points like I did earlier when I was graphing polar coordinates. So my first point here is an angle of 0 and a radius of 3. So that means when I stand on my origin, when I turn my body 0 radians, so that means I'm facing the 0, I'm going to move 3 units out. So that means I'm going to land at this point. Now, when I actually draw and connect, it's going to kind of be like a loop, something like this. And you can see this connection right here, over here on this grid, where you start at the 0 and you go to the positive 3. And that's what I'm doing here. I started at the 0 and I went to the positive 3 in the positive direction. Now, I'm going to go to angle pi over 4 with a radius of 0. So basically, I'm just going back to my origin. And since here I'm decreasing back down to 0, that means I'm coming from here, I'm coming back towards the 0, creating kind of like this petal looking shape. Now I have pi over 2 and negative 3. So that means I'm going to look at the angle pi over 2, but since it's a negative 3, I'm going to go in the opposite direction of pi over 2. So that means I'm going to land here. And then I'm going to create part of my petal. And then my next one is 3 pi over 4 with a radius of 0. So basically I'm just going back to the origin. And then my next one is an angle of pi, and I'm going 3 units or 3 radii out. And since it's a positive, that means I'm going in the direction of pi. So it feels kind of weird going, feels like you should be having a negative 3 here, but it's not. And I'm going to create my other part of the petal. And then for the next angle, 5 pi over 4, I'm going back to the 0. And then for my next angle, 3 pi over 2, but it has an opposite radius, so I'm going to go the opposite direction. So I'm going to land here. And then 7 pi over 4, going back to the 0. And there is my petal shape polar grid. Now if you want what it actually looks like, it looks better like that versus my hand drawing on the computer. All right, now let's try another one, and I want you to try this one on your own. All right, so you're going to graph r equals 7 sine 2 theta. Let's see how you did. So you set the argument 2 theta equal to pi over 2. So I'm going to go in increments of pi over 4 again, just like before. I'm going to plug in each one of these into 7 sine 2 theta to get the following values. And I'm going to first graph this on my Cartesian grid. So it'll look something like this. Now I'm going to go ahead and translate this to my polar grid. So when you're done, your polar graph should look like this. So for this one, I started here at the 0, 0, and then I went to angle pi over 4, which is approximately right about here, and I plotted 7 out. Then I went to pi over 2, plotted 0, and so on. 3 pi over 4, which is right here, but -7, so I'm going here, and so on. And I keep going until I have my completed graph. All right, let's look at this one, where r equals 6 plus 4 sine theta. So this time, theta is just going to be in increments of pi over 2, which is nice because it's going to be a shorter chart. Plug in these theta values to get the following r values. Now when I plot these on my Cartesian grid, I get the following graph. And when I translate these, you'll get a graph that looks like this. All right, let's try this one. R equals 1 minus 3 cosine theta. So theta is also going to be in increments of pi over 2. When I plug in these theta values, I get r's to be -1, 1, 4, 1, and -2. So the graph of this one on the Cartesian grid looks like this. Translated to polar, it will look something like this. Now, this leads us to two very special polar curves. The first one are what are called rose curves. And these are in the form of r equals b sine a theta or r equals b cosine a theta. And both of these have rose curves. The rose curve has 2a leaves, petals, if a is an even number. For example, r equals 5 cosine 6 theta tells me that I'm going to have a total of 12 leaves or petals. So if I was to count these, I would have 12 petals. Now, the rose curve has a leaves, petals, if a is an odd number. So for example, if we have 5 sine 5 theta, that just means it has 5 petals. And the leaves / petals have lengths of b because that helps us get your radius length. Now the second type are what are called limacons. And these are in the form of the graphs where r is equal to a plus or minus b sine theta or r equals a plus or minus b cosine theta. These are called limacons. Now, if the absolute value of a divided by b is less than 1, then the limacon has an inner loop. So for example, if we were to look at the graph r equals 3 minus 4 cosine theta, we have an inner loop right here. If the absolute value of a divided by b is equal to 1, then the limacon is a heart-shaped graph called a cardioid. I think I pronounced that correctly. For example, r equals 3 plus 3 sine theta, and it kind of looks like this. So it has this little dimple in, so it kind of looks like an upside down heart-ish shape. Then the next type is if the absolute value of a over b is between 1 and 2, then the limacon is dimpled. So for example, r equals 3 plus 2 cosine theta. So it doesn't go all the way in like the heart-shaped one. It just has this little like dip right here. And if the absolute value of a over b is greater than or equal to 2, then the limacon is convex. So for example, r equals 3 minus sine theta will look like this. Basically, it looks... Well, I hope you enjoyed learning about polar coordinates, and I will see you in class.